Okay, yeah. So this is the first number on. This is the first lecture on number theory, and so yeah. And so the first exercise will be with integer bases, or well, just bases in general, really. So, oh, another. Okay, so yeah, so to the person who just came in. So this is the first lecture on number theory, and so first of all, do all of you know what bases are? Okay, well, if no one responds anytime soon, then I guess you do know. So, okay, I'll just assume that you know. So, yeah, I guess you can start trying this problem out. So when you're done with this question, just send me a private message with the answer if you do. Okay, so now I'll start going over this problem. So we want to find the number of ending zeros up to the 14 factorial in base 9. And then we want to express our answer in terms of base 9. So then basically, if we want to find the number of ending zeros of 2014 factorial in base 9, we basically want to find the number, what we first need to do is find the number of factors of 3 in 2014 factorial. And so the way we do this is rather well known. It's just through the floor of 2014 over 3 plus the floor of 2014 over 9 and plus the floor of 2014 over 27, and then do the same for 81, 243, and finally we do it for 729 as well. And the reason you don't need to bother with anything else is technically this formula would go on to infinity, but at this point you can just stop because everything else past this point would be 0. So if you just calculate everything, these numbers are just okay, sorry about that. So this is just equal to 671 plus the floor of 2014 over 19, 2014 over 9 is simply just 223. And then what you add next is the floor of 2014 over 27, which is 74. And then the floor of 2014 over 81, which would be 24. Then the floor of 2014 over 243, which is 8. And then the last one, the floor of 2014 over 729 is 2. And so if you add everything up, you'll just see that this is exactly equal to 1002. And so that means that the number of factors of there are exactly 501 factors of 9. And so that means there will be 501 ending zeros. But this is in base 10. So we need to convert 501 to base 9. And so all of you already know what bases are, and so I won't really bother explaining how to do the conversion. And so you just get 616 base 9. So yeah, that's how you do this question. And
Wait,
so now I'll move on to the second
quick question.
Okay, yes.
Why do you divide by 2?
Oh, why do I divide by 2? Because this number is the number of factors of 3 in the number, but you want to find the number of factors of 9. So basically,
Okay.
yeah, so you're just dividing by 2 because a factor of 3 does not correspond to a factor of 9. You need 2 of them. So any other questions? Okay, well, if not, you can move on to the second question, which is about modular arithmetic. So modular arithmetic is relatively famous, so I will assume that all of you already know what it is. And if not, it's basically it's kind of just like remainders, but like a more standardized study of it. Okay, so I'll start going over this problem now. So for this one, so one of Euler's conjectures was disproved, blah blah blah. Basically, you're trying to find the n such that this equation holds true. So yeah. And so we want to find the value of n for which this equation holds true. Okay. So first of all, we can notice that for the left-hand side has 2 evens, 2 odds, and so that would mean that n is even as well. Because the sum of because the sum of 2 evens and 2 odds is even itself. And next, by Fermat's little theorem, you have the n to the 5th is congruent to n mod 5. And so for using this, you can find n mod 5. And it's just 3 plus 0 plus 4 plus 2, which is 4. And then next up, we can use mod 3. So n to the 5th, we can just see is directly congruent to 1 minus 1 plus 0 plus 0, or 0 mod 3. And so that just means, yes, you can use Chinese remainder theorem for larger numbers, but this is just like one of the possible methods. I'm not saying that this is the only method, I'm just saying one of the methods. But most of the solutions will probably use Fermat's little theorem and Chinese remainder theorem. So yeah, so in this case you have that n is 0 mod 2, 4 mod 5, and 0 mod 3. And so that just means that n is 24 mod 30. And so clearly n is greater than 133. So n is equal to 144, n is equal to 174, and so on. So now after this, to determine the exact value for n, you can just, first of all, you can notice that the next possible value will be 204, and 204 to the 5th would definitely be way too big. And so after this, you're really just left with one of these two values. And at this point, you might be able to tell that 174 is still too large, or you can just or you can start checking, and well, eventually you'll you'll realize that the only answer is one possible answer is 144, and that's the answer. This is just done by eliminating, just because their other possibilities are way too large. So yeah, does anyone have any questions for this problem? Okay, well, if not, let's move on to number 3. And so once again, this problem is modular arithmetic. Okay, so I'll start going over this problem now. Okay, so yeah. Okay, so let R be the set of all the possible remainders when the number of the form to the n is divided by 1000. So we want to find the sum of all possible R. So yeah. All right. So you can see that x is congruent to y mod 1000 if and only if x is congruent to y mod 8 and mod 125. So now we see that what we want to find is the first two numbers I and j such that to the I is congruent to the j mods 8 and 125. And so, but then we also need to see that, oops, j, and I and j are greater than 2, and that's because the remainders of 1, 2, and 4 will not be repeated mod 1, 8 afterwards, because everything for I and j past 3 is definitely 0 mod 8. So now we just need to focus on I being congruent to j mod 125. And so I is congruent to j, oops, to the I is congruent to 2 to the j mod 125. And so, okay. Well, anyways, okay, continuing on. So basically, we end up seeing that 2 to the I, whatever, repeats mod every 100. And between that, everything is distinct. So we can see that basically the minimum I and j are I equals 3, j equals 1. And so after that, basically we're just trying to find the sum from to the 0 to the 1, so on, to the power of 102. And after this, everything starts repeating, so it's unnecessary. And so this sum is just equal to the power of 103 minus 1, because it's just kind of a formula for the sum of consecutive powers of 2. And so this is congruent to 8 minus 1, which is 7 mod 1000. And so the answer to this question is 007. Right. So if there are any questions, please ask. And if not, I'll move on to the next question that regards divisibility and divisors. And so once again, if you have any questions, ask. And if you get any answers anytime, please send a private message with your answer. Okay, so I'll start going over this problem now. So let n equal 2 to the 31 times 3 to the 19. I want to find the number of integer divisors of n squared less than n that do not divide n. So first of all, n squared is equal to 2 to the 62 times 3 to the 38. And so that means that it must have 63 times 39 factors. And so you can group all of these factors except for n itself into pairs such that one is less than n and the other is greater than n. Simply put, it's like taking 36. So you pair 1 36, 2 18, 3 12, 4 9, and then 6 is in a group by itself. It's just like this. And so that means that okay, anyways. All right. Thank you for coming, I guess. Okay. So yeah, so the number of divisors is 63 times 39 minus 1 over 2. And so this is the number of divisors that are less than n that divide n squared. And so of these, there are 32 times 20 minus 1, which is 639 factors of n. And that's because every factor of n clearly would divide n squared as well. So the answer is 1228 minus 639, which is just 589. And so that's the answer to this question. And so if you have any questions, please ask. And if not, then let's move on to the next question. And for this one, there's really no answer, so just provide like a quick sketch of the proof if you actually get an answer. All right, I'll start going over this problem now. So we want to prove that this fraction is irreducible for every natural number n. So yeah, so basically this is the same as showing that GCD of 14n plus 3 and 21n plus 4 is equal to 1. And so this just simple, and so you just repeatedly apply the Euclidean algorithm. So this goes 7n plus 1, 14n plus 3, and then 7n plus 1, 7n plus 2, then and this is just clearly equal to 1. And so basically that's it. So yeah. So now let's move on to the next question. So for this one, you just kind of just send another sketch of the proof if you get an answer instead of an answer because they're all right. So I'll start going over this problem now. Okay. So we want to show that the sequence is eventually constants. Mhm. Okay. So we'll do this through contradictions. So assume that it's false for some integer n at least. Okay. And so then that means that there is a smallest n, which we'll just call b, for which the statement is false. And so clearly b is not 1. Sorry. And that's because b is not 1 because the numbers are all the same mod 1. They're all technically 0 mod 1. And so, yeah. So next we note that for all integers b, that would mean that 2 to the 0, 2 to the 1, 2 squared, so on, would eventually, no, this holds true for all integers b, and so the sequence would eventually become cyclic. So we have a b the period of the cycle, and so there are k minus 1 non. I mean, there are k minus 1 non-zero residues mod b. And so we have that 1 is, so basically k is between 1 to b minus 1. And so since 2, 2 squared, 2, 2, 2, so on, does not become constant mod b, that means that it must follow the sequence of terms 1, 2, 2 squared, 2 cubed. Oh, sorry, not 2 cubed. 2 to the 2 to the 2, so on, does not become constant mod k. And so that means that the problem statement does not work for n equals k. And so since k is less than b, this is a contradiction because we have already assumed that b was the smallest one. And so that means that the problem statement is true and the sequence always eventually becomes constant. So basically the main idea was to proceed through proof by contradiction and then assume that something was the very smallest possibility for which something was true, then show that something even smaller holds true, and that's the contradiction, and so that's how we get this problem. And so now let's move on to the final problem for today. So, yep, so once again, if you have any questions, please ask, and if not, if you get the answer to this question, if you get a response to this question, you can just send an outline. Okay, so I'll go over this final question now. Okay, so yeah. So we let P. So basically want to find all possible AN such that this is true. So let P divide N be the smallest prime factor of N. So then we have that N is equal to Q times P minus 1 plus R. And that would mean that the GCD of R and P minus 1 is equal to 1. The given condition basically tells us that P divides A plus 1 to the R minus A to the R. So now we let G be a primitive roots mod P. So G is primitive roots mod. And so we have that the sets G squared to G to the power of at P minus 1 gives all residues except 0 mod P. And so we can let X and Y be between 1 and P minus 1. And so we have that G to the X is congruent to A, while G to the Y is congruent to A plus 1. And so we can do this because G is primitive roots. And so that would mean that P divides G to the XR minus G to the YR, which would mean that P divides G to the R times X minus Y. The R times X minus Y minus 1. And so that means that P minus 1 divides R times the absolute value of X minus Y. And so P minus 1 divides X minus Y, which is definitely at most P minus 2. And so this is a contradiction. And so that means that there are no primes that divide N. So N is just equal to 1. And if N is equal to 1, any value of A works. So that's the answer to this question. And so thank you for coming, and I hope all of you have a nice rest of your weekend. So thank you and bye.